Good morning everyone, my name is John Telemarque and I'm one of your BIOL SIs for the quarter. So we're just going to hop right into it. So for today's video we're going to go over lectures 3 and 4. And the main thing that I wanted to go over to start off with is electronegativity. Electronegativity can be defined as a tendency of an atom to attract a shared pair of electrons toward itself. So what's the importance of that? Electronegativity can determine whether something is polar, nonpolar, or ionic. So I have a table down here that's going to actually show some examples regarding if something's nonpolar or polar. So down here, I have CH4 right here. And CH4 has a carbon molecule or carbon atom, and the carbon atom has an electronegativity of 2.5. And it's bonded to 4 different hydrogens. However, we're just going to look at one hydrogen. So a hydrogen atom has an electronegativity of 2.1. So if we subtract them from each other, we actually get a 0.4. And as seen down here in the table, 0.4 is considered nonpolar. Nonpolar. So the next example we're going to look at is water, and water has a H2O bond. So oxygen is bonded with 2 hydrogen atoms. However, we're just going to look at the OH bond. Oxygen has electronegativity of 3.5. And it's bonded to hydrogen, which has an electronegativity of 2.1. So if we subtract that, it has a 1.4. A number of 1.4, making it a polar bond, polar covalent bond. So the next thing we looked at is actually the atom carbon. What makes carbon so special? Well, carbon itself has 4 valence electrons, meaning it could bond to 4 different things to complete its octet rule. So carbon itself has 6 total electrons, but the thing that makes carbon so special is that it's able to make a single bond, a double bond, or even a triple bond. So as shown here, I took pictures from Google of 3 different examples of either single, double, or triple bond. So right here, you could see that carbon is bonded to a hydrogen and it's only sharing 1 valence of electron right here, and the hydrogen itself is sharing its valence electrons. So that makes it a single bond. Single. But the next example right here, carbon is actually sharing 2 of its electrons with another carbon. So right here, they're both sharing 1. And right here they're sharing another, so that's 2 sharing, making it a double bond. Even though there's 4 electrons in the middle, each carbon atom is sharing 2 of its own valence electrons, making it a double bond. And another way to write it is actually this way, and the way on the right is actually more preferred because it's a lot easier to write or draw. And then the last example is a triple bond, and the carbon could either triple bond to another carbon, and another example is the carbon could triple bond to nitrogen. So as shown here, carbon is actually sharing 3 of its electrons, and so is nitrogen. Okay, the next thing we're going to go over is line diagrams or line bond notations, and this is actually a lot simpler than it looks. So if we were to look at this first example right here, so the first thing we would do is look at how many carbons there are and then compute that. So it's actually very, very simple. So to make it into line bond notation, you start off with a point, and from this point you make a line. So you're like, what the heck? What's that? So right here, what did we just draw? That's actually 2 carbons so far. So now we just need to draw the next carbon. So then this carbon right here, and that's how it's going to look like. And then from each carbon, there are hydrogens. So we just got to know that carbon bonds to 4 things. So this carbon on the left, it's bonded to 1 other carbon, so you can only draw 3 hydrogens. The carbon in the middle is bonded to 2 things, so you can only draw 2 hydrogens. And the carbon on the right is bonded to 3 things, so you could draw 3 hydrogens. So in total, how it would look like is just look like a simple V. And that is equal to the thing on the left. So if we were given line bond notation, how do we make it into a chemical formula? So the first thing you would do is actually count the number of carbons. So there's 1, 2, 3, 4, 5. And then from each carbon, we draw how many hydrogens are connected to it. So we can see this is connected to 3. This one is 3. This one is 3. This one is connected to 3 carbons, so it's only connected to 1 hydrogen. And this carbon right here is only connected to 2 hydrogens. So then what would be the chemical formula for this? So since there's 5 carbons, and how many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 hydrogens. So now I want you guys to try the next example, pause the video, and okay, now we're going to start solving this question. So the first thing we do, like last example, is draw the carbons, and then we connect it to hydrogens. Wait, what the heck is the thing in the middle? The O is considered an element, so that's oxygen. And since there's two lines connecting carbon to oxygen, that's a double bond. So we know carbon right here is connected to 4 different things, so we cannot draw any more hydrogens because that would break the octet rule. So then that's our chemical formula. So this example has 3 carbons, it has 6 hydrogens, and 1 oxygen. So that's how you write the chemical formula. The next thing we went over in lecture 3 were different types of isomers. So an isomer is the same chemical formula but different structures. So the first example is a structural isomer. It has the same formula but has different arrangements. And in line bond notation, I drew 3 of the same chemical formula but differently. So if you were to see them in real life, they would not look the same, however they have the same chemical formula. The next type of isomer is a cis-trans isomer. And in order for something to be cis or trans, it needs a double bond. If it's single bond or triple bond, it's not going to be a cis or trans. It has to be a double bond. That's extremely important. It has to be a double bond. And a cis, right here, this would be an example of a cis. Cis means that the elements that you're focusing on is on the same side. And then trans, that means they're on different sides. So it's trans, since they're on different sides of the double bond. And then cis is the one on the left since they're both on the same side. So the next example is enantiomers, and up here it says enantiomers are mirror images, and it needs to be connected to 4 different things. It needs to have an asymmetric carbon. So an asymmetric carbon is something that's connected to 4 different things. If it's not connected to 4 different things, then it's not an asymmetric carbon. So we're going to look at the first example here. So I actually have 2 examples for us. So for the first example, we're going to look at the carbons and see if there's an asymmetric carbon. So we're going to look first at the first carbon. And this first carbon would be considered an asymmetric carbon because it's actually bonded to 4 different things. So it's bonded to a hydrogen, a chlorine atom, a hydroxyl atom, or a hydroxyl molecule, and then everything else here. Why is it everything else? Because in order for something to be connected to it, it's everything connected to that one carbon. It's not just that carbon next to it. So that is one asymmetric carbon right there. So then we're going to look at the atom to the right and see if there's an asymmetric carbon. And like before, the asymmetric carbon is actually right here since it's bonded to 4 different things. So since they both have asymmetric carbons, now we're going to see if they're mirror images of one another. And they are actually mirror images of one another. So that's what makes it an enantiomer. However, I drew 2 carbons just to show an example. This carbon right here, would it be considered an asymmetric carbon? No, it would not, because it's not bonded to 4 different things. It's actually bonded to 2 different hydrogens, making it not asymmetric. However, this molecule, it's an enantiomer of the other one because it does have an asymmetric carbon. So for example number 2, this one right here, it's not asymmetric because it's bonded to 2 of the same things. So this carbon right here, even though they are mirror images of one another, this carbon is actually bonded to 2 of the same hydrogens, and this carbon is also bonded to 2 hydroxyls, which are the same exact things. So we went over 7 functional groups. In lecture, the professor actually went over them in detail, so I want you guys to look at that. But these are the 7 if you forgot them. So this is regarding lecture 4. We had carbohydrates and lipids. So first, before even looking at what carbohydrates and lipids are, we have to look at what monomers and polymers are. Monomers are actually individual molecular subunits that make polymers. So polymers are made up of individual monomers. So there are actually 3 different types of polymers: carbohydrates, nucleic acids, and proteins. However, lipids are not considered true polymers because they're made up of non-similar subunits. They're not made up of the same subunit. So they're made up, for example, we're going to go over in detail later, but lipids are, for example, they're made up of glycerol and fatty acids, and those are 2 different things. However, like carbohydrates, they're made up of the same thing, like monosaccharides. So in order to connect 2 different monomers together, we actually do something called dehydration synthesis. And dehydration synthesis is pretty much when you have 2 monomers bonding together and a water molecule leaves. For this example here, I used two different glucoses, and they have the formulas that you should know, C6H12O6, and if you add them both together, the formula should actually be C12H24O12. However, since you're losing a water molecule, so you're pretty much losing minus a H2O, then that's what makes this formula appear. If you have any questions, go to SI and we'll go more into detail. So the last thing I'm going to go over is carbohydrates and lipids. Our professor actually went super into detail regarding each one, but here I actually have a summary of everything, and I really recommend you guys to do this when you guys make a study guide, or just when you guys are studying, just to break everything down, because all the information itself can be overwhelming, but if you break it down like this, it'll be a lot simpler. So carbohydrates, as I mentioned earlier, they're actually, the monomer for it are monosaccharides, and an example of a monosaccharide down here is glucose. So the next thing, if you were to connect two monomers together, such as two glucoses together, that would be considered a disaccharide, and disaccharides could be an example down here, glucose plus glucose equals maltose. And the last thing that's very important is a polymer, which is polysaccharides, and that's just multiple monosaccharides connected together. And some examples of that is on the right, starch, glycogen, cellulose, and chitin. I'm not going to read the definition for all you guys, but you guys can read it yourself. But the main things that you guys just need to know, that it's for energy storage and for support. Those are the two main things regarding polysaccharides. And the bond for itself is glycosidic linkage. Even though it is a dehydration reaction, the linkage itself is like very specific just to carbohydrates. So it's a glycosidic linkage. So the next thing we went over was lipids. And lipids are not considered true polymers because they're actually made of different subunits. So for example, the first thing we went over regarding lipids are triglycerides. And triglycerides are made up of glycerols and 3 fatty acids. The next thing we went over were phospholipid bilayers. And phospholipid bilayers are extremely important. These phospholipid bilayers are made up of phosphate, a glycerol, 2 fatty acids, and an R chain. And the last thing we went over were steroids. And steroids are actually things that are composed of 4 fused carbon rings. So these make up steroids. This is a phospholipid bilayer. And this is triglyceride. Okay. So the last thing we're going to go over is saturated versus unsaturated. But even before that, I wanted to do a phospholipid bilayer and why it's extremely important. So phospholipid bilayers, they have hydrophilic heads and hydrophobic tails. What does that mean? As we learned in lecture 1 and 2, hydrophilic means something that is polar. Something that is polar could be either ions or polar covalent bonds. So for example, we could have water, or we could have even ions such as like NaCl, because these are all polar and they have charges. However, hydrophobic is something that's considered nonpolar. And an example of something nonpolar could be fats, or for example a CH3 bond. Something else that could be even considered nonpolar are two elements that are bonded together. So for example, if you had O2, would that be polar or nonpolar? They'd be nonpolar because electronegativity would be 0. Yeah, so the last thing I wanted to go over were saturated versus unsaturated. Saturated is actually, it has no double bonds and it's packed tightly together. So it would be connected to a glycerol molecule. Pretend you had a glycerol right here. And this glycerol molecule is connected to 3 fatty acids. 3. So meaning that it's packed tightly. So there are no double bonds. So that means these glycerols would look like this. But then unsaturated, that's when a glycerol is connected to 3 fatty acids, but either one or even multiple could have a double bond present, but it has to be cis. So then it would look like this. You have a glycerol right here, and it's bonded to a fatty acid. Oh. and that would just make it look a lot more weird. So unsaturated, it's cis double bonds, and then saturated, there are no double bonds, but it's packed tightly together. So yeah, that's pretty much it. If you have any questions, come to SI session and we'll go over this more into detail. Thank you.